So let us start the tutorial session. So in this session, we have seen a couple of problems. So far we have talked about solid mass theory in this conventional way, and some of the things like ENN and SBN, SBR for solving different type of problems for predictions. So in these
tutorials I will share the data now, and the problem needs to discuss that we have talked about that resistivity inversions, one problems on that how we can get that optimal model parameters, let us say the true resistivity of each of these layers and true thickness of the layers for a vertical rectical sounding data. So it is a 1D problems, but still it suffers from lot of non-uniqueness, and we will face that problems that how the problem of singularity, problem of say rank will face when you are inverting that G matrix. And so the data we will share now. That will be your problem first. Second problems that one data set will be shared from the Mentala basin of Southeast Indian Ocean. So there, from the data of oil log, we need to solve that the problems from log to predictions of your say water saturation. Say one of the properties we estimate in many of our reservoirs that from the log to say let us say these water saturations. So here this data need to see that if there are any outliers, you need to check statistically, then remove the outliers, then need to calculate the volume of the clay, then porosity. These are the associated things to formulate this, and so you need to exercise this for ENN and SBR, let us say, these problems. Let us calculate these and then develop the predicted models from log data to say water resource, water saturations, and see the predictive capability of models like ENN, SBR, random forest, and see the different type of statistics, how we can compare the different type of say mean square error, say L2 based norms, mean absolute error, L1 based estimates, Pearson correlation coefficient R square coefficient of determinations, and then see that how they are ranked in terms of your performance. That is what your problem 2 is. And some of the guidelines is provided. We need to take these inputs of your say photoelectric effect, porosity data, density data, sonic, and need to predict this water saturations from the log. Training and testings divisions is provided. We need to train these models in this 60% of your randomly sample say training data, and this is your testing. And so some other data set will be provided of nearby wells, and there we will check that similar exercise to the predictive models. That is what my problem 3 is. And problem 4 is a gravity inversion. So with the help of these damped least squares methods, a gravity data along a profile has been provided, and fitting that observed versus predicted, how we can get the optimal parameters, simple models of buried sphere of density, then depth and the radius of the sphere. That is what has to be find out optimally, and that gives that once things will be optimized, then need to also calculate all these parameters, like what will be the radius of the buried sphere. Let us say what is the density of the buried sphere, because the density contrast will be helpful to fit that anomaly, gravity anomaly of the sphere. Then related statistics like mean square error between the observed versus predicted, then standard deviation. All these statistics can be reduction of errors, and then index of agreement. These are the other statistics to see that how your predictive models performs in the case of your qualities. Let us say how your optimal model parameters is accurate for this type of problems. Okay, some of the equations, this formula has been provided, how to calculate this correlation coefficients, index of agreement, and reduction on error. These have their significance because when we will do this type of comparisons, we need to also understand that how this type of indices or statistical measures are influenced by the outliers present in the data. So let us say that although all these all these things are actually measures that how your predicted things is good or to the observed one, but still all these statistical measures again perform different way in a cases where things are noise free, things are outlier. If the things is the noise is predicted data is perturbed with the amount of the noise. So in that cases, we need to also understand that what is the hypothesis of this, all the statistical measure from where it has been derived. So let us say we have to have talked about the L1 and L2 norms, and then both will be, both may perform different way. In case your noise model, in the case observation is noisy, or observation is noisy in terms of more disturbed by the outliers data. So in that case, we need to also see that how we can interpret all these statistical measures. Well, these are the required for your justifying that how good your AI/ML models to predict that observations or the estimate they need some parameters which is derived from the oil log or any other geophysical data. So I will sharing the data sets and some of the theory on the slide. I think we have shared it, that like resistivity inversions, that what is the theory of calculating that forward response. And if it requires, then we'll share further some paper where these things are there. Western Maharashtra, and so the data is a Schlumberger resistivity sounding, which is very good for explorations of your groundwaters, mapping of different contaminant plumes, like say, saline water intrusions and many other geo-environmental mapping problems. And it is a very quick and low cost survey to get that how the true resistivity of the earths are from the electrical, geoelectrical sounding. So there are two electrodes, so A and the B, they are the current electrodes. So current has been injected into the ground. Now the distance between the potential electrodes here M and N, and this depth of the point of investigations is the center between M and M. And this is the center point of your profile. Usually the spread length is 200 meters. So from the center it is 100 meters. And so at a point, these configurations allow that changing the current electrode spacings as well as the changing the potential electrode spacing. And by injecting the current measures the voltage. So there is a formula that from the potential to that the formula is saying here that del V is the change of the voltage, G is the geometrical constant, I is the current. So the apparent resistivity of the earth can be computed. And then our inverse problem says that from this apparent resistivity data in the geoelectrical survey, we need to find out that true resistivity of the layers and the thickness. And it is a vertical electrical sounding, so the assumption is that our mother earth, it is a layered, and it consists of the number of the layers. They are horizontal. These are the assumptions. And there is no variation of the resistivity laterally. So that is one of the assumptions which that vertical electrical sounding is very good.
Which type of value is displayed?
Vertical electrical sounding means it is Schlumberger array. So Wiener array and dipole-dipole array, pole-dipole array, and they are hybrid combinations in 2D systems. So this BES or this submerger sounding, things are that when your mother are the horizontally layers and you want to estimate that how your resistivity variations is vertically, longitudinal, means how it is varying from the surface to the inside the earth. If you want to know that vertical variations of your resistivity, then Schlumberger will be the better one in compared to the Wiener one. Wiener captures better resistivity variations of your lateral variation. Now, if you want to capture this lateral as well as the longitudinal, then there is a combination called Wiener Schlumberger. In resistivity imaging system, say that there are many commercial equipments are there imaging, they inherited the concept of the seismics of a bin size, and the combinations of your electrodes, like here current electrodes and potential electrode, but in their system it is a multi-electrode system. Multi-electrode systems means they are interchangeable. So that current electrode can be acted as a potential electrode and vice versa. And there are a different type of sequence can be created to capture that you want to exploit only the Schlumberger soundings, or you want to explore the Wiener, or it is a combination of the Schlumberger Wiener, any other dipole, pole dipole, there are many configurations are there. That is a system of 2D system, the acquisition system. But here we are talking about the inverse problem with the data set which is a VS sounding data, where this concept is a 1D, means your resistivity variations only we are looking at how it is varying longitudinal, means from the surface to the inside the earth. And from that we can have a good and quick solution about that how our layers are there. And it is very effective because suppose for groundwater explorations, we want to know that where the groundwater is available, water table depth, etc., etc. And very quick way, then this type of survey is a good. In fact, it is a low cost survey to get that the position where this water table is there. And it has a lot of societal application in environment. Okay, so this equation is saying that if you see this top equations here, apparent resistivity rho A, it is a function of S. S is your spacing. It is a spacing between electrodes. It is a function. These variables actually define that spacing between the electrodes. And this is integral equations, and T is your that transfer say functions which actually contains the physics of the information of the layer earth. So this T is the recurrence relations is there that for a multi-layer cases, multi-layers means as many numbers of layers you consider, number of the layers which contains the fill up the full homogeneous half space, that defines, and lambda is your variable here. Okay, that is variables, and J1 is the say first order basis functions that combines that how this T, which contains the informations about the thickness as well as the resistivity of the each layers, and that in the subsequent equation you see that how it is related with the different layers and contains the information about the physics. Now it is highly nonlinear because by changing this, say H is the thickness of the each layer, lambda is your integral variable here, and it is a tan hyperbolic function, so it is a tan sigmoid, nonlinearity comes, and by changing this, say small value of your rho and the H, it may change that nonlinearly the apparent resistivity. So the problems here, it is that from the apparent resistivity data which is there in your sounding, we need to find out that H, the thickness of the each layer, and the rho, this is the true resistivity of the each layer. Okay, so these equations has been the forward relationship, And then the inverse relationship is that here you see this is your del M, this is your model parameters, and it is the expressions of your inversion relations where G transpose G is your kernel operator relate between the models and the change of the data vector del D. G transpose G plus beta square I. Beta is your damping factor. What is the data?
Delta N.
Data is change of data. Change of observations. Here data is your raised apparent resistivity.
Which parameter is this? I mean, is it this resistivity?
Apparent resistivity. In the resistivity, yes, it is apparent resistivity.
What is delta N?
Data is the model parameter, true resistivity.
Okay, that's true resistivity and this is
Apparent resistivity. Apparent resistivity from the survey, we get that resistivity of the combination of the whole layer. So there are two more layers in between.
So what you get from the survey is that
Apparent resistivity.
and then you get it converted to
Resistivity, the true resistivity from the conversion process.
So which is the thickness?
Thickness is the thickness from the surface to the layer. So
But in that one, which one is the thickness?
it will change.
But there is no thickness in that equation at that time.
In the integration, in the inversion equation. In the inversion, which is inverse problem, there are two parameters we have to estimate. One is that rho corresponding to layer 1, each one corresponding to the thickness of the layer 1. Rho 2, true estimate of the layer 2, H2, thickness of the layer 2.
But then delta M is both thickness as well
Yes,
as
rho is the model parameter, they complex all things like thickness and resistivity of the each layer. They all put in a cell vectors.
excuse me, sir.
How is the true resistivity from the inversion be a true resistivity while there is an assumption like there is no variation of resistivity later on?
So resistivity can be vary in the whole body. Because we can vary non-linearly and laterally. But in this configuration, there is a limitation. So here we are assuming that there is a variations only vertically. It is there, but we cannot take into account in this approximation.
Arises if there is that assumption, how comes that true resistivity is a true resistivity?
So it is a true resistivity, but you see, our mother earth is complex. Okay, we formulate, we provide the theory so that in the best or the maximum way we can describe the data, right? Now things is that this relationship is so complex, maybe the whole mathematics also may not capture these things. That is the one limitation. Maybe the problem of the physics, what of the physics we are assuming it, that may not be sufficient to describe your observation. So these are the limitations is there in every theory. So let us say we estimate, say for example, volume of your some standard body, like sphere, like rectangles. So in that cases, we know that what is the length, what is the width, there is a formula that can able to find out the exactly the volume or periphery. Now let us say one ore body is there, which is a fractal in nature. Fractal means they have their zigzag periphery. Now any formula, geometrical formula is there which can exactly compute this, their periphery. So there is again the approximations are there. The dimension takes into the center. How you are actually finitely discretize this periphery, then only the accuracy will affect it. So these are there, even mathematics is there, even though we are trying to see that maybe we have a lot of anisotropy is there, lot of assumptions, things are there. We have to assume it or rule out some of the things so that we can make that mathematics more simplify to get the more and reliable information. Okay, so that the del M actually contains the information of the true resistivity of the layer and the thickness. Now the question is how many layers, how many things are there. That is up to the interpreter. They have to play with that. Say it is a 3-layer case or 4-layer case, and accordingly provide the initial guess about the resistivity value. Then only it will able to calculate the apparent resistivity, and then fitting will start, observed versus prediction. And these equations already discussed that role of the damping. You see the singularity may arise it here also, and the rank deficiency problem of G transpose G. That is why the damping has been included in those equations to make that more definite, and so that this inverse of the whole part can be obtained. LQ, okay. So this G is the matrix, let us say, it is the relation between data and the model. You remember that D equal to GM, so many times we have discussed about. So that G, here this G is actually that we need to actually decompose it because of this problem. So this part, if you see, this one. Okay, if the beta is 0, it may happen the problem of the rank deficient problems in small scale in many cases, and the beta will have that flexibility with taking into the positive value so that at least inversion can be obtained. And this part has to be estimated, then only we will apply this change of the data to get this model parameters here. And this beta, change of this beta can be follow that how much we should take. Initially, if you take the high value, then the iterative way that can be have some exponential functions so that the subsequent value will decay down, will be small. That gives you the idea about that, how UQL. So this G has been actually decomposed with the help of singular value decomposition, SVD. So this G can be expressed in a combination of 3 matrices, UQL. U is a orthonormal matrix, Q is your diagonal matrix, L is again a orthonormal matrix. So the fact that the U and the L and the Q, these will be helpful to understand that whether the G, how many eigenvalues are very small or close to the 0. If the eigenvalues of your G is close to the 0, then the instability will come. And you will see this, you will get that inverted result very absurd. It may not be explained by the geology. So let us say density, resistivity of your some value is very absurd, means it may not be geologically possible. This type of things will come because of these small eigenvalues in your G. So in order to avoid this and how many eigenvalues are there, we actually decompose this G matrix in terms of the 3 matrices, U, Q and the L, and by seeing their distributions, we can see that eigenvalues which are actually arranged in the Q. Q is your diagonal matrix. So this eigenvalue, the highest will be at the first, and it will be arranged in the way that lower panel you can see that the value of the eigenvalue of the Q. And if it is small, then the problem will come. If it is a negative or 0, then this problem will be unstable. So there is a ways out. One is that by using this damping is the one way, because whatever the value is there, once you are multiplying adding this beta square into I is your identity matrix. So what will happen? The beta square I will directly add to the diagonal elements of your Q matrix. So if sum of your value is very low, so beta square I, that is a value, small value, but it is a positive, and that will add to that brings the stability in that G matrix.
Actually, the first two equations yeah, rho A of S and T of lambda.
This is the integral equations. Integral equations, then how?
The resistivity of the each layers is related to your apparent resistivity. Integral relation.
Okay. What is T, sir? T of lambda? T?
The capital T, is a transfer function, which actually contains the information about that. It is a recurrence relation. So we transform that information about that, how resistivity of each layers is related to the apparent resistivity. So in a layer of models, you see that there is a number of the layers. So each layer is having their resistivity and other thickness. Now how this apparent resistivity contains the information of all the layers, because the sounding you see here, you are making the sounding in this point. Here you are expressing this oriental. But below that there is actually a number of the horizontal layers you are considering again. And each layer is having your resistivity state. H1, H1, Rho 2, H2, like that. Now we are considering this linear case, linear case, that is the problem or the data we can see that what type of layers is actually required, how many layers are required to explain the observation in the mass case. Then we need to be that with this arrow to get the interactivity and how it is approached, that is what is called resistance. And the interactive process will be getting that some value which gives the resistivity between the rho A is observed one with the computed one. Rho A, this is the compositions. This relationship actually, once you use it theoretically, this will give the computed value theoretically with these relations. And rho A actually appearing to another rho A data set, what is there in the table. It is linked to inside is data in your what we call the spacing, and the next one, the rho A, the apparent distribution at each of these points, this are actually known. I was in the WhatsApp group.
So what is the name?
Name is just written, I think it is
M1. That's the data set.
so you want to get for resistivity, data set extend time for gravity, and then for SDM and overall data it is from.
It is an Excel file that
Okay.
Sir, in the T of lambda, rho is that is 2 raised to. I mean,
Rho is the apparent distribution.
rho x.
Rho is the true of each layer.
Okay. I mean, before this minus sigma of gets checked, they will be using that one before that. I mean, what is the difference between that one and this one?
The rho is the
What is the difference between first two equations and the second two equations?
and the second two equations is actually for 2D case.
Okay.
Okay, actually it is showing that we see is sigma.
the conductivity. It is a function of X, the profiling Z. Actually, what happens this once this current is injected in the plane, okay? So we cannot restrict that in a one plane. So original equation is actually 3D. So we are injecting the current. So this current can flow the least resistive path according to the Ohm's law. We cannot restrict it, okay, you flow in this plane. Right? They will follow according to the least resistive path, what Ohm's law says. So what happens that it is originally the point is a 3D. So in the all directions, these currents will flow it. Now we are probleming this 3D problem to solve in a 1D plane. Seeing that our variations of this resistivity, it is in the plane where we are saying the vertically only. But in the 2D plane, you are actually giving the freedom to another one. So it can vary in Z directions as well as the X direction. So the plane. Then originally this current is actually in a 3D concept. It is injecting. Now only these problems we are restricting to this 1D domain. It's a second
Second equation you see,
There is no
sigma, it is actually given a conductivity. So you must have to give the rest of what conductivity. It is a function of S conductivity. S is your
why there is no y, sir?
Huh?
Why there is no y term?
why that is 3D. So this is a plane we are considering. This is a S and this is a J. One. So this part is now. So if the S is J is there, then it is a J. So where we are talking about J means it is a 1. Means what we are assuming is J it is a 1.
But in delta V there is x, y, z.
And delta V is actually these potentials. It is actually the concept which is 3D. Okay. But we are estimating
conductivity in 2D, right? But exactly this current you are injecting physics, it is in 3D, for the current wave. So potential will develop in the 3D way, but we are measuring along a line or along a plane. And their distribution sigma that is expressed in that. So once this sigma it is x, y, z, then it will be a pure 3D problem. Your basic equation is this. You see this current is a x, y, z. And this is your original equations, and then it is a transform to your the domain. So these two lines actually not the 1D case. This two line, del and this del. Two lines actually related to the 2D problem.
One, two, three, four, and then some numbers. What are units for those numbers? What are they?
So
Usually that this resistivity inverse problem, you see that we can okay, so this is how this is yours different layers. Okay, so the first one is you say rho 1, this is the H1, the problem is rho 2, H2, rho 3, H3, rho 4. Okay, so usually if you have a 1, 2, 3, 4 layer case, so how many parameters you are having in 1D? 1, 2, 3, 4, 5, 6, 7. Because last layer, it is assuming that it goes up to infinity. So if the 4 layer case is there, your number of the parameters your 1D resistivity sounding is, this is your 4, 1 less your thickness. Because last layer thickness, it is touching the last. So here you have the less. So your problem will be like that. This M, say let us say M is each contains the both, say R and say T, thickness, or H. This is a vector. Now R will be your, say, rho 1, rho 2, rho 3, rho 4. If you are considering a 4-layer case, you are assuming that, okay, this data sheet will, 4-layer case will be sufficient to describe your observation. So you take this a 4-layer. Now in order to define this 4-layer, what are the parameters is required? Rho 1, resistivity of the each layer, first, second, third, fourth, and this one is the 3. This is the thickness. Now your M contents of R and T, say, let us say, R is the true resistivity. So true resistivity will contain, say, rho 1, rho 2, rho 3, rho 4. And thickness, say, or H, contains H1, H2, H3. So finally, initially you have to provide this initial guess of rho 1, rho 2, rho 3, rho 4, if you 4-layer case, and H1, H2, H3. Then compute this rho A theoretically and see this how this computed rho A is matching with the data we have provided with the observed one. And it is a iterative process to get that. So there are a lot of commercial softwares are there. In fact, some.
Like there is 1, 2, 3, 4, 5, and then 358, 338, 242, 261. What is that? Yeah, is that resistivity or what?
No, the data is
Sir, by using inverting by using some software, okay? First of all, we are inverting the apparent resistivity to determine the true resistivity of some areas. And by using, we have apparent resistivity as well as true resistivity now, okay? Can we develop the relationship by using between the apparent and true resistivity by using machine learning? We can do that like that also.
That is what we have discussed about that Acha. So here it is like that. Which is A, the one A. This is actually even by 2. It is a meter. This is in A by 2. It is a meter and this is your
Spacing.
A by 2, the electrode spacing. And this is the rho A. Apparent resistivity. 4 meter.
Now we have to invert it.
So this is your observation. Okay. Now we have to invert it to find that true resistivity of the layer. And if it is a 4-layer case, we need 3 resistivity value, 1, 2, 3, 4, and H1, H2, H3. If it is a 3-layer, 1, 2, 3, and H1, H2. If it is a 5-layer, 1, 2, 3, 4, 5, H1, H2, H3, H4. Those 5th layer it is
actually reaches up to the infinity, means the bottom of the subsurface. Yes.
Marvin is suggested. Sir, may you please show up the way you approach the problem, so as we can compare the role of each approach, like how the sounding worked and how the machine learning worked. So because of for the sake of time and for the sake of understanding.
Okay, so I will give you some
examples in the PPT. Then you exercise on that and see that how good it is. Yes. So this is a standard curve just to see that this is the curves, theoretical curves which can be seen at a first glance. Okay. So this is your, say, 3-layer cases where rho 1, rho 2 and rho 3, and if the rho 2 is more than the rho 1 and rho 3, we can expect that this type of apparent resistivity curve with respect to the spacing AB by 2. So this is a K-type curve, and then you see this is a H-type curve where first layer resistivity is high in compared to the second, and again the third layer resistivity high in compared to the middle one. So that will give you the H-type curve. For A-type, it is the curve you see this, the rho 1 less than rho 2 and rho 3. So it is a ascending curve. And there is a curve Q, it is a descending. Here rho 1 is greater than rho 2 and rho 3. So this is the standard curve, you can expect it for your 3-layer cases. Now if you move to increase this number of the layers, because 3-layer case may not be explained the whole data distribution, in many cases it may happen. So we need to see the combinations of the K, H and the A, Q to get their distribution. It may happen your apparent resistivity is high, low, then again high, again low. So in the combinations of your types, we can assume or we can formulate that what type of layers are there and what are the combination of this one. This is the basic things about that VS curve. How to see that if your H-type curve, then your first guess should be rho 1, the first layer resistivity should be higher than the rho 2. So whatever this, you just take the guess, that should be accordingly. Then only you will get some first guess about that, what the observations looks like through the computation. This is a theoretically curve generated by the masters. Some curves are there based on the equations can be generated. So essentially you have to guess first the initial models, then that the computing the what you call it is that forward response. Okay, computing the forward response. So you will compute this or predict it through the true models. Then we have the observations which is provided in the data. Then misfit has been computed here. Then this gradient descent, the Jacobians can be computed. Then the last part is the singular value decompositions based damped expressions, inversions expression, which will give you that whether your estimated model parameters can able to have the true one or no. SBT is singular value decomposition. That what G matrix is decomposed in the combinations of the U, Q and the L, the 3 matrix. That is the SBT.
The application will be to decompose this G matrix to see that whether you problems is there in your invertible matrix. Okay, so this is the page which is applicable
in Python. There are open sources there. So there the first is that forward computing. So this is actually the code which provides you that forward computations of your resistivity. So 1D resistivity models. There you will see these are the Q, F and M. They are the coefficient which is solved with the filter theory. There is a book by D.P. Ghosh which actually solved these problems and published in the Geophysical Prospecting long back in 1971-73. And still this is one of the very effective way to see that how this forward response can be done. And this is the relations you see this with the help of the filter coefficients. This code will allow that forward computation means how this recurrence relationship has been computed, that earlier code. The second is the Jacobian calculations. Here we have that Jacobian's functions that takes that AB by 2. AB by 2 is your apparent this electrode spacing between in the Schlumberger. X and R and T is the true resistivity and the thickness. These are the parameters rho A and the rho A1 actually the apparent resistivity, the computed one, and this code will allow to find these Jacobian calculations, and finally you have that we have to provide the resistivity value. So this is your true resistivity. Let us say this is my initial guess. Okay, this is the true resistivity and this is the thickness of that problem. So let us say and provide this, then using this code it will allow to first compute the recurrence relationship, then compute this rho A calculated. This rho A will be compared with this data provided in the Excel file. This is your observed one. Then compute the loss functions. Then this Jacobian, this G matrix will be there. That G matrix will be decomposed with the help of this SBD, and the computations will be. So this is a one iterations work. Then in subsequent changing the damping factors, it will take and it will again allow to get it the subsequent, and finally you will get that RMS and other fitting. So let us say we have to take the initial value, say let us say what we have, and with this first we will compute this rho A computed one, and we have the observed one with this data, and it will try to match it. So it is a what type of curve it is?
So this is a similar
curves, and from that it is actually see that whether it is a 4-layer cases or 3-layer cases can solve these problems, that you have to play. You have to play with that. That here you see this 1, 2, 3, 4, 5. Let us say it is 5-layer cases considered. So in that case, the 5 resistivity and the 4 thickness value we have to enter it, and then you will see this how they are. This is your initial models, and this is the inverted model. How you can explain that the observations. Okay, this we have to play and see that RMS value of this observed versus predicted one, and see this which one is the gives you the best by changing the damping factor, because this in these equations this damped least squares inversions has been used, and that can be done. So we'll share the MATLAB code. Those who are using this MATLAB, they can do this exercise. And
code in the code one slide before Jacobian
true resistivity, and the thickness T is the thickness, LR is the I think some iterations coefficients are there, and rho and the rho is the apparent resistivity. I have to see this what the variables are there. Okay, so next problem is. So is there any doubt, or you can do that? Huh?
Solve the equivalence of different problems. Equivalence of different problems different problems. Here the equivalent is here. Means by combinations of your rho and the H, you can able to compute the same rho. So let us say that it is a 3-layer case. Let us say.
So, or it is a 4-layer case, or it is a 5-layer case. So it may happens that by combination of the rho and the H, you may get it that the same observation. So it is a equivalent problem is there. So from that approach we cannot resolve it. Only way is that that you just try with the different combinations, say 3-layer case and 4-layer case and 5-layer case, by changing this row and the thickness value, and see that is there any ground truth value or any true resistivity records available outside your experiment. Let us say that suppose in that particular area it is a hard rock. So if it is a hard rock, then usually the geological sequences, hydrological sequence is that top layer, maybe it is some spoil or laterite at the most. Then after that there will be maybe a clay or clay media where in this our Dhanbad and this area belongs to. Then after that is a metamorphic succession will come. It is a hard. Basement will be hard. So usually we will say that your first layer is moderate and then again low and then there will be high, and this is the sequence. Now you see, depending upon the geology of the day, so that type of information may be useful to guide your resolving this issue. So if you see this in the geology that okay, up to say 10 meters, say shale is there, let us say, then you know from the textbook also the knowledge that what is the resistivity of your shale, what is the resistivity of the sandstone, what is the resistivity of the laterite. They have their range. So from that also you can resolve some of the issue, that say up to say that layers how much the resistivity is there. Okay, whether it is a fitting with this one, because this it is equivalent problems. Equivalence problems cannot be solved by the physics. Okay, if physics could have handled these issues, they could have done with the mathematics. It is the problem limitation of that. So we cannot resolve it, but we can give as more trials and errors, and by incorporating some of the prior state of information. Prior state of information is such that, say suppose in your 4-layer case is fitting, is giving the good fitting, but your top layers resistivity, inverted resistivity is coming out to be unrealistic, whether you will accept or no, because you see in the top layer it is showing some very absurd value, but the geology is saying that it is a soft layer, it may not be that much of resistivity. So that way we can rule it out. So this is the use of your a priori set of information or geological information we are taking outside of your experimental setup.
Okay, I will share the photos.
So G, how we will find?
Capital G.
Yeah.
Capital G.
For the electrical resistivity program.
So from that capital G is so this
Here, so in the Jacobian it is there. J is the Jacobian.
Even only then we can use the inversion.
So let us come to the programs we have shared. So the data what I have shared, that first job you have to load it here. Okay, then they will ask for the resistivity and the thickness. R is the true resistivity and T is the thickness. So let us say it is a 3 layer or 4 layer. Accordingly, you have to provide. If it is 4 resistivity value will be there. If it is a 3, like that. Then it is the M is your model parameter, which takes that both the information R and the T. And the initial iterations will start. That all these mean speed precisions, all are set maximum iterations. Then it will compute that forward response. So VS1 MOD, this code will allow you to find that the forward response of your forward computations basically with the help of that subscript, the subroutine, which is actually, so the control will be there. This code, these functions will be used to compute this, the G, and here you will see that some of the parameter which is required, say Q, F and M, these are the filter coefficient which has been derived by the DP course. There is a book is there. That coefficient directly has been used to estimate the computations, the forward. Then so it will, the another part is your Jacobian, then this Jacobian is the J. So these functions will allow to compute the computing the Jacobian. So once this forward response has been there is observed. So misfit will be there. So this first derivative, partial derivative of this misfit with respect to your model parameter with the Jacobian, the J will be computed with these functions. Then this that singular value decomposition application such comes that the G matrix shall be decomposed with the help of your three matrix. One is U, S and the V. U and the V is the orthonormal matrix. S is your diagonal matrix which contains the eigenvalues of the A matrix. That is G here. So it will allow you to control that whether this problem is suffering with instability or it is a rank related problems. So from checking these eigenvalues of this the G, where the S will give you that whether it is a rank deficient problem or no. Then this beta, which is the damping, which is taken into account. So beta is a term is there. So it is a beta square I. I is your identity matrix. It will directly add to this that S, diagonal elements of the S, and finally we'll compute that with that iteration rho A. So it will compute this, the difference of that rho A, say let us say rho 1, rho 2, rho 3, like that. It will compute and it will compare with these observations and see from the plot also you can see this different value of the beta. Say beta is a damping. Different value of the beta, you can compute it and see this how your observation is close to your predictions. That way you can get some trial and error, and by changing your iteration automatically, so there will be initial value and then final estimated value, and these things has been plotted with the, so there finally we'll get that this is your apparent resistivity, which is your observed one, and this is computed one through the inversions with the help of optimized rho and the R, right? And finally we can see also that this is your initial guess and this is your optimum model parameter distribution, and this is the y-axis is your depth and this is the sounding point. So the vertical variations of the resistivity can be obtained through the damped least square based inversions provided the given VS sounding. So this is one case, and for the other data again we have to do this is the standard damped least square based inversion scheme to find that optimum modem parameter. So if you just run this, so it will compute it. There is a beta control, and so by changing this initial model parameter through which you have given, you can see that how your observed is fitted with the, how your prediction is fitted with the observed one. Now coming to that problem of second one, where this data has been shared. This is a open source data of IODP programs, where this basin is very close to Australia, and there is a geological complexity to find that possibility of gas hydrate, etc., etc. So our job is that given that data, which is two sets of data we have provided of the same the nearby wells. One is the U1513A, and the other one is that U1513. So from the data we need to see that what are the data are there. There will be a different sort of records. So depth value is there, sonic is there, sonic.
Sonic cloud.
Sonic is you. Intercontracting. This is
Matrix, that density value. This is the photoelectric effect response, photoelectric effect, and this is also another density, because the density can be measured by the different geophysical logging tool. Say one is your density, another is the from the gamma also. Some relations are there, through that you can get the density. This is the, some are natural gamma. There are varieties of these response tools. Response are there. Yes. So these records we have to use and to find that what are the, first plot it and see this if there are any outliers are there, and how to remove that outliers. There are various ways are there statistically also see that that quartile informations, that how many things are beyond that. From that you can tune the data of the outliers, and what we have to use that some of the petrophysical informations is required to find that the theoretically calculate this. One is that gamma ray response. This is the geological logs, geological successions, which is standard. And if there is a quartzite is there, limestone is there, dolomite is there, then what will be the density log response? And this type of information is required to have that different type of interpretations and calculate the relations that say how we can find that the lines, say cell volumes, clay volumes, and what is the lines so here the formula required to find all this petrophysical density, porosity may be calculated in a different way. Directly there is a neutron porosity, there is a density porosity, so different petrophysical formula.
This is a most and most substitute. This is a fluid. So this is your rho. Rho is the density of the fluid. Okay. This is your matrix.
So usual concept of this granular mediums, that there is a matrix, the solid part we assume that it is a devoid of porosity, and there is a porous space, and usually we define that matrix have a zero porosity and pore space only whatever the porosity is available. So the Archie's formulas are there to relate that the petrophysical relations with this what is the value of the rho ma. This is the said that the density of the matrix, rho b is the density coming from your the log, rho ab is the density of the fluid, and again the rho ma. So rho ma value also, if it is a matrix of the different geological succession, so rho ma we have to take according to the value, whether it is a 2.65, 67 or any other. Rho ma is a matrix density. So if it is a
So that depends on that compare this, the data has been required.
Geological. Phi is your porosity. Rho ap you know the fluid. But again this there will be slight variation. Say if it is a saline water in oceanic setting, so there will be a slightly it may change it.
So later on is one calculated of that on each one. So lot of additions. No, language assign one answer. Tomorrow I will get answer. So another problem I need to discuss. To complete first one. So just need another 5 minutes.
How to determine water saturation?
Accuracy.
Water saturation.
Water saturation. Water saturation is say in a rock. There is a matrix or there is a
Volume of water divided by total volume.
the formula in one. So the formula is there in Archie.
Okay, Archie.
Yes.
Archie formula is to determine porosity.
Water porosity again related to water saturation, there is a formula. It is improving percentage. So those who are living for the first time, maybe some So not necessarily that you have to install all these things. So that atom also you can run it, that whole Python script. And but you first in the sense net connections has to be there. So you can put all these programs in your drives, and from that you can run. You need to log in the Gmail, perhaps its availability is your account. You can locate the drive. If you want to create a new drive, you can create it, and there you can put all the scripts as well as the data. You can create the new data, new folders.
So rho m is the density of the matrix. Rho m.
Rho m is the density. Rho m is the density of the matrix. Rho
NRHB?
rho m is from density log.
In the problem, NRHB is there
I mean the density of the different tool. That is the density part.
of the different tools.
But we have the first one, that amount density.
RT integral of the density.
Only the first second part.
That is the density.
That is the half density.
First is the formula.
Bulk density log. So people need to access the drive.
That's all.
So we need to use some of the libraries or pandas, NumPy, and sklan. And we have been inbuilt some of the
It's already in package. And for plotting purpose, matplot library you can use it. Need to mount this drive and the data access. You can print and check what is the not a number, the whole data set. Then read that the gamma and other logs. The best of the inter-quartile relations, you can set that from the histograms. You can identify that types of layers, out layers, and you can set and remove these. Then from this gamma ray, we can have the idea about the cell baseline. From the volume of the cell, clay can be estimated from the rocks. Porosity also can be calculated. Then you need to see that their relations and if there are any value which is not convincing, we may check it and remove it through filtering. Null value also you can check it, remove the outliers, then develop that prepare this data sets for your predictions. So it is your mapping from your log to water saturations, let us say. By combinations of these also you can find that which combination best fit gives your regressions, best regression. You can see with the different optimizations method what is available with these machine learning tools, Adams. You can experiment with the different transfer functions. By combination of the which things actually gives your best accuracy. Formula to calculate the porosity. This is the formula from the density logs. You can calculate the porosity.
We use metrics and we use the point, that is the log density. The way you are attempting for the density inversion problem, the density-based code may be used for inverting the radian over Paris parameters. So there is a standard geometrical body used.
We use it for explaining the observations, the anomaly. They can be your sphere, can be horizontal cylinder, can be vertical cylinders, rectangular prisms, and by their combinations. So what actually these needs that anomaly is recorded by the equipment, and in the inverse problem start with that we need to find out the density contrast, which is actually causing this one of the factor to create the anomaly, and the depth and the size. Size is governed by the radius here for your buried sphere, and z is the depth variable. So the anomaly natures, their amplitude is governed by these three factors. One is that density contrast, another is at what depth the causative body lies, and third is that the size. So if your size is more, then accordingly your response curve will be take the shape. So from the observations, here your data, a set of say anomaly along a profile, what we have given, we need to find out that the density, depth, and the size. So that is one of the problems we solve in academics, that how to find out the model parameters. So let us take an examples of your gravity response, which is recorded in a milligauge, and let us say that a buried sphere at different depth. So what it matters that from the surface to the center of the sphere, that is your depth, and at what points it is observing, and the size. So depth, size, and the density. These are the parameter has to be estimated from your observation. So here this del G is your gravity anomaly component, and let us take a sphere. So the formula we can able to calculate the del G, right? Now the data which it is provided, it is the gravity anomaly along a profile, and let us say that causative body at the center, and see first what is that anomaly of along a profile, and see whether it is the nature. And the first case is that what type of geometry can explain that particular anomaly. That is your first step, we have to attack it. So if it is a sphere, or it is a cylinder, or horizontal cylinder, or vertical cylinder, or fault models, or any other geometry. So let us say that it is a response which you are guessing that it may explain by the buried sphere, let us say. Then your model parameter to be estimated is the depth of the buried sphere from the surface, the density, and the size. Size is governed by the radius of the sphere. So that three things has to be estimated from your given. The problem we have said that we have given the data set along a profile of your gravity, and using that code, say damped least square based inversion code, we need to find out that what is the best way we can fit that observed versus predicted. So this code, it is a similar where you need to provide the radius, density, and the depth, and so it will compute this forward response with this value, say gravity, which gives you that this is the location. X0 is a location at the center. G is the gravitational universal constant, and G is the response, del G. This is the anomaly that has been computed at any point along a profile. So this response is the forward computations will give you that anomaly given that initial model parameter you have provided. Now once this computation has been done, this will match with the data observations along a profile, and then inversion process will start. Then once this loss functions has been defined, then the Jacobians will allow you for computing this gradient based optimizations method. And this response is showing that, so let us say you have taken a initial guess and it is very far away from the optimal, you may land up with this type of response, that gravity anomaly, it is too far from you initially. So it is a trial and errors, and that with the help of damping, you will see, let us say in the different second or third or fourth attempts, and see how your observation is close to your calculations. So in this way, you need to fit that best fitted models, and that give you, it is optimal. What is the optimal? Optimal means it not necessarily that always it will be a minimum or the maximum. It will be a combination of these things. It may happen that in these equivalent problems, what we'll see that by the combination of these things, you may get say solutions, a combination of the solution all are solution, but which one will be the peak? That again, it is a problem of this non-uniqueness, many of our potential field problems like gravity. So gravity is one of the problems where we will face it, that density contrast and the depth. Both the things we cannot resolve at a time uniquely. Only we can make certain about their product, density contrast and the depth. We can measure the multiplication of these two parameters, but not the individually. So that is why different way we can tackle it by gradient descent, say global optimizations, sampling, Bayesian approximations, data-driven modelings, with the help of prior state of informations, like suppose you guess it and C land up with a set of model parameters which you are satisfied at the time. But that type of estimation also should be explained by the geology, because finally once you give the solutions, the geologist will ask for drilling, or the petroleum reservoirs will take over that, say what is that things, what is the potentials, estimations, etc., etc. So then ultimately what will happen, the drilling the last stage, and it assumes a lot of cost. So if you provide the wrong information about the depth, their spatial distribution, means shape, all are related to that, the volume. If the volume estimation is wrong, then it will be a huge loss for employee, because
like it's difficult to get the depth or the density individually. As a rule of thumb, is normally obtained in a combined format. Now, how will the geophysicists recommend about the depth?
So there are this type of things here, because most of our geophysical observations are based on the universe method. So there is no direct machines that can give you the one regular solution. Okay, so one thing is that one approach is that you combine multiple data sets if they are compatible. Compatible means they are consistent variable. Let us say you are using sensitivities. You need also say electromagnetic networks in that case. Say some of the properties, there is electrical property that is overlying part, that is overlying electrical conductivity related parameters. What are that conductivity, let us say? Water saturation, water. So these are more sensitive materials. These are not precisely ordered by the electrical method. Okay, but if you are going for the structural related information, then if you are not satisfied with the gravity, then you have the magnetic. If you are gravity, they are similarly function and they can have the control of the structures. But if you want to see the fluid properties, let us say, so you can take these electricals and materials and you have these some number of your things to be more helpful too. So one way is let us directly not giving the, so let us say, answer about that. Then you go for the magnetic, if it is that. Or any other geophysical methods, you can see what is the layer properties. And see the consistency of that. That is one approach. Then this biological information, let us say that one body, you need to bring in the geological knowledge, either in system, either in readable data. So reading is very costly here. Reading means there wells, readable, and collect the sample directly from the date. And that sample also can be distributed in the lab. Okay, what is the water circulation of that sample? What is the velocity of the sample? What is the density of the sample in the lab? So you are collecting the sample from the lake of the mother earth and directly measuring their physical property on the lab. So we are having these at least the depth part. Because directly you are accessing the sample from the depth. So there are two things. One is that sort of identity problem you are solving. So the identity is the density contrast and the image. Both cannot be easily determined. What unity can be determined? That they are multiplicative factor. Now suppose the density contrast is here and E is in a factor. Now you want some sample from some date. Then the date parameter required is certain because that is control of you. Because you collect the data from the date directly. So this type of uncertainty can remove it from that. Now once date parameter is you are sure that then other parameter can come. Because right hand side is no. Left hand side is a sum of the both. So right hand side is sure in the result of that part. In left hand side there is continuation. So if one parameter you are able to access directly from a sampling inside the R, then other parameter will be better way to control it. That one can resolve this equivalent problems what you are asking about that. But the worst is that everywhere we can bring it. So these particular cases we want to see that. Because it is impossible and not impossible. But if there is everything that we are
Companies are there, say, private or the government PSU, they have a drill hole data in most of our machine. At least not in the world, but in some part, everywhere there is some information. So if this information is available, then it will be helpful for better control it. But again, drilling is the last option. Everywhere you do not get, because collecting the sample, again put it in the lab, that requires your cost of your measurement, labor and other things. And it is intensive also, because every depth, every centimeter you are collecting the sample and measuring this parameter every time. That is not possible for a huge amount of your case. That is why this geophysical methods is quick and non-invasive way to assess this physical properties variation. You see, if the drilling, if you are able to do every part of your world, then other things may not be required. But the amount of the samples you are seeing, this is not possible physically to measure these things, considering the volume and the area of your survey. But what is happening, or what the potentiality of the EIML is that, suppose you take an example of your small case where you have the geophysical data, surface data, as well as the drilling data. Now develop the machine learnings and try to map that if my physical property of surface data with the drilling data, and develop the regression model. So the information means mapping from this one domain to the other, if it is possible for a small block, then same thing can be predicted or extend to a nearby, provided the geology should be similar. So that is the one limitation we associate with all EIML. But if the geology is similar, I do not think there is any other alternative method rather than EIML tool which can serve you better than anything. This is the best one we can say, and it is a quick and cost-wise it is. That is why industry is looking for that. So we have a reservoirs, we have a data for particular wells, and there is some other area where data cannot be acquired because of the logistics. There may be a river, there may be logistic problems of the local problems. They are not allowing to go there to deploy the equipment. So there are many areas are there, sensitive areas are there where we cannot survey it. So EIML can have some idea about that in some part. Say one side of your survey, you develop it to properly train that EIML models, and with this proper training, with the possible scenario, you are considering that may be distributed your whole reservoir, then this may be immediately apply to the data where things are not controlled, or some of the parameters is missing, or some of the things we could not able to directly collect it. So that is a potential applications on that. So that is a established things. Only the problem is that the geology is changing rapidly. If the geology is uniform, I think this is one of the good tool, because If you go this deeper into the earth, there the geological variation, most of the cases it is a follow the long structural trend. But the problem will be the near surface, where the changes of your geological strata is more rapid rather than your deep process. So let us say if I run this, so let us say this is I 100. So I am giving the radius of the buried sphere, then the density, and the depth. So let's see. So this is the showing that this is your observations, and this is the first case, how it is away from your observations. This is in kg per MKS unit, meter cube. So the fourth problems we have that discussed about this gravity. So along a profile, this data has been provided, and this SBT code which is we have shared for the resistivity, it is for same for your gravity problems, and with that we need to come up with this, which is what are the optimal model parameters, and with this optimal model parameters you need to also compute this all statistical information to have that what is the fitting, whether it is a order of the fitting like a mean square error between observation and the predictions, mean absolute error, Pearson correlation coefficients, and R square is a coefficient of determinations, standard deviations of these all types errors, RE reduction of the errors, the index of agreement, the formula has been provided. So here you see this P bar. So this is the average value of the prediction. So in Pj is the any value, the observed value, and the predicted value, and this is the average. This is your observed one, Oj, and this is the average value of the O. Okay. And this vertical bar is your absolute value, mod, L1.
The correlation coefficient, sir, is like it's working in two variables. What if in case we are having more than two variables, like Pj, Lj,
It is actually the vector.
So observations, it is a vector. It may contains the value.
two vector forms. My question comes in the form like, what if we are having something like 3 or more vector parameters, vector parameters?
No, this PU is a predicted value. It is the predicted value of the radical one.
Okay. So it will be a value only that contains along the profile. So you have a say profile how much? Say 20 points, let us say. Say against the 20 points, you will get this p value at the 20 point. So it is the difference between that observed versus prediction at the each point.
OJ.
Origin is observed. J is your substitute, IJ, and origin observed, and B is the predicted.
So can we go for it?
What?
So can we go take a look at the machines because it's already 5:30.
Okay, so anything you need to discuss? Otherwise, we will close today.
So if anything is there tomorrow, there is a sessions there also, we can continue that, right? And the today's lectures and the materials already shared. So you do this exercise and see that how closely you got the answer. I have the answer, at least some range I have. So now we are closing today's session.